So our second talk in the session is going to be from David Hollman, Sandia National Labs. And he's going to be talking about porting the mini array application to Charm++.
Well, thanks very much. I am from Sandia National Lab, as mentioned. I also want to thank Martin for introducing my topic somewhat by talking. I'm part of Janine's group at Sandia, and we are working on learning about what runtimes, by runtimes I mean asynchronous mini-task runtimes, are going to be most useful in the future for the national labs as a whole, particularly for the DOE national labs. I know there are quite a few different runtimes being used across the labs right now, and so we're trying to kind of consolidate and figure out, for porting large applications, what is the best path forward. So I'm going to introduce my topic and talk about the process of writing the code. This is more of this is partially a feedback to the Charm community as to what it looks like for us to pick up the Charm runtime for 3 months, port this miniature application to it, and what are the kinds of patterns that emerge and such. Then I'll have a little bit of performance results just to show that we actually did it and talk about what's next. This work's been done as part of the project, which, as I kind of described in the introduction, is this exploratory phase for the asynchronous mini-task runtime that'll be used at the National Lab. Dharma has meant many things over the past few years. The project's evolved a little bit, and it used to mean something else that made a lot more sense, but now we have an H in the middle of asynchronous, and but it's distributed asynchronous adaptive resilient models for applications. I don't think we figured out where to put commas yet either. So the mission is to assess and address the fundamental challenges imposed by the need for performant, portable, scalable, fault-tolerant programming models at extreme scale. I promise I won't read every single slide like this, but wanted to make sure I get these things right, because these are things written by people way above my pay grade. So the main 3 focuses of our assessment are programmability, load balancing, and fault tolerance. I think our emphasis on fault tolerance has been a little bit greater than most other similar projects, and so having that as one of our main points is somewhat interesting to people. So there's 2 portions of the project. We're doing this comparative analysis portion, which is what I'm going to be talking about 1/3 of right here, or less than 1/3 of, but I'm going to be talking about the Charm++ portion of. And then there's another portion where we are actually writing a prototype runtime that kind of incorporates all of these things, and from there we're trying to learn what could be added, what could be subtracted from various existing runtimes, or are we going to go ahead and implement our own? All of that is a little bit up in the air at the moment, but yeah, I just said that. So for the first year of this research, we're assessing 3 different runtimes. Oh yeah, I didn't say, the idea is that we're going to use these mini apps that are developed by domain scientists as kind of a model or a prototype of something that really addresses the difficulties involved in writing their application in parallel. That's the goal, at least, of these mini apps. And so our first 3 runtimes are this, and then our first mini app that we've got for assessment this year is Mini Arrow. Obviously, we want to branch out into other mini apps so that we aren't too narrowly focused, but basically this first year is kind of a proof of concept that the assessment can work with 1 mini app and several runtimes. We want to do a few more runtimes. We definitely want to do a few more mini apps. So that will be coming in the future. Here are a lot of the people that have helped us. Legion is at Stanford. Obviously, you've heard about Uinta, and obviously Charm++ is here. All right, so Mini Arrow is, at its core, like I said, a proxy app that illustrates common computation and communication patterns in unstructured mesh codes. It is a 3D unstructured finite volume computational fluid dynamics code. It does all of these things that are listed in those bullets. The important part for discussion here is that first bullet at the very top, and things like this. The baseline application was only 3,800 lines of C++ code. Give you some idea of what we're working with. It's the actual meat of the code is significantly less than that, but because the structures, data structures and such needed for Cocos, because it uses template metaprogramming so heavily, the data structures are not exactly terse, so you end up with a lot of setup code for Cocos. It's a brilliant code, but yeah, Cocos has already been introduced to, so that'll save me some time in my talk here. The Mini Arrow itself, part of the reason why we want to look at a lot more mini apps. In this particular case, there's very little task level parallelism, and this on the right-hand side is a task DAG of the of Mini Arrow. You can see pretty much nothing can be done in parallel. Pretty much everything. I mean, there is significant data parallelism. Don't get me wrong, but they're independent, heterogeneous task parallelism is not heterogeneous in that sense. Is not a big. There's not a lot of big gains to be had there in this particular mini application. The communication is ghost exchanges on an unstructured mesh, so you can't just say, okay, well, we'll set up 3D mesh. We know exactly that we're going to be communicating to A, B, and C. You have to keep a list of the neighbor, and you have to keep a neighbor list that could be different sizes for each worker. Yeah. So this project started with a boot camp about 3 months ago or so, March. I guess that's really only 2 months ago. And these two people, Nikhil, I'm not going to try and mispronounce, Nikhil and Eric, helped us came out to Sandia, and we worked for about 4 days. There were about 10 Sandia scientists in attendance, and since then we've really had one scientist working about 50% time and a couple others working 10 to 20% time. To give you an idea of how long it's taken to port this mini app, I mean, so it's not a significant amount of time. Currently, we are running and passed the Mini Arrow test suite. Most of the, I say immediately apparent optimizations, you can always optimize a code more, but we are pretty much, I mean, that's a little misleading. We're pretty much done optimizing the Mini Arrow code as it is. There are certain things that we can dig into, but we're much more interested in either looking at other mini apps or looking at some additional features like vector parallelism and with CUDA and the SMP version, which doesn't work right now. CUDA, Cocos is, ironically, at least the version we're using, not thread safe. So that is an issue. All right, let me talk a little bit about the coding process. What was easy? Well, load balancing, which can be an absolute nightmare, especially if you ever tried to do it in MPI, raw MPI code, was very easy. I say load balancing, synchronous load balancing. There are certainly a lot of interesting problems to be addressed from the runtime side for things like work stealing and such. This particular mini app, those sorts of features would not be super interesting because there is a significant amount of temporary data that is present during the time step that you'd have to migrate, and you'd end up with work stealing would not be very efficient. There's also not enough load imbalance in this app to really make those things. But again, that's why we want to look at multiple mini apps. The code for doing this, if you've never done such a thing before is basically 3 or 4 lines in the CI file. You just stick it in, synchronous load balancing at the end of a time step. And checkpointing, similarly, very easy. Just call. Once you have everything, all the relevant objects serializable, pubbable, they call it. Same thing, the in-memory checkpointing, which is a form of resilience, but is as has been already introduced, which is good. I don't have to harp on this point. It is still checkpoint restart resilience, which is not ideal. It would be nice to have some sort of message logging, but in this case, again, you're talking about codes that are doing 100 to 1,000 time steps. You know, having to roll back one time step is, you're talking about 1% of the application. We've got a little ways to go before we're having 1,000 failures in one application run, but it certainly is something to think about for the future, and people are doing. So that's good. Both of these, both checkpointing or resilience specifically and load balancing, as I already introduced, were key features of the asynchronous mini-task runtime systems that we wanted to look at. And both of these were essentially done within, I'd say the first day, basically that first 4-day boot camp where, I mean, if you've ever done coding in a group of 10 people, that's pretty impressive because it can go pretty slowly. And the key here is that both of these, the thing that both of these have in common is that they're both basically a result of writing puffers, right? Which is a nice thing, that all you're doing is serialization on your side, and the runtime is handling everything else. So, oh, shoot, I should be keeping track of time. Okay. Assume I started at 11. Okay, too slowly then. All right, so the MPI, the kind of quick start implementation of going from MPI to charm is, for us, was pretty straightforward. You just take one char, and map it to an MPI process, or vice versa, one MPI process to one char. So you're basically thinking of MPI processes as chars. That obviously doesn't, I mean, it gains you quite a bit. You still get the you now get the checkpointing, you now get the load balancing to some extent if you want to over-decompose. But you're still fundamentally writing code that is SPMD, synchronous, all of the downsides of MPI too. But you basically send message-like function calls on proxies of array members, and receives become when clauses. So you go from code that looks like this to essentially code that is split into 2 different functions. You kind of do a split of functions between your send and receive. At least that's kind of the pattern we saw emerging. There are several issues there. Static variables don't work the same way if you do that, because chars can now share the same process, whereas MPI processes, the static variables are unique. Conditional communication, you obviously can't split 2 functions in the middle of an if statement, so you have to do something a little more clever there, not a lot more clever, but that simple pattern doesn't really work in that case. And another thing to look out for, I guess, that we lost a fair amount of time trying to figure out, so part of this whole discussion is that the person who originally wrote Mini Arrow is now not at Sandia, so it's a good experience in porting over old code, because the person who wrote the code is no longer there. So we spent a lot of time looking at these different MPI sends and realized they were basically just sending size data, and you don't have to do any of that in charm, because you can set the size data comes along with the function call. You don't have to say MPI receive this amount of data, because it comes along with the message. All right. The question about that is, is this necessarily the best approach to sit down and say it? Because if you start with MPI code and you do a straightforward one-to-one port, are you going to end up with basically MPI code? And is that worth the effort? We can debate as to whether or not that's worth the effort. There are certain advantages of that, but do you end up with these unnecessary synchronizations that are much harder to dig up compared to if you had kind of taken a top-down approach and looked at your application, looked at what it's doing, written out the task flow in the structured Dagger code, and filled in the application code from there. So it's a question of more or less copy and pasting. Clearly, the top-down approach, you're going to end up with fewer synchronizations because if you're starting with a task and trying to come up with dependencies of it, you're actually more likely to miss dependencies than you are to add extra dependencies. Whereas the other way around, the bottom up, you're going to end up forgetting to remove dependencies, if that makes any sense. But for production code, a top-down overhaul is completely impractical. We have to start thinking about what is the middle ground between these two. And most importantly, really, you need to sit down, I think, before writing any code. Something that we learned from this project is before writing any code, you really should sit down and assess to what degree do we want to overhaul. Can we get away with overhauling this entire function? Or do we want to actually rewrite this entire class? Or do we want to just copy over parts of this entire class? That assessment actually needs to be done, is the more important point. How to actually do that is a little more difficult, but that's the point I'm trying to make here, is that it needs to be done. Templates. So the speaker before me mentioned that they liked Charm because there were no templates. We didn't. There is template support in Charm. I don't want to imply that at all, for those of you who have not tried to do it. But let me talk a little bit about Cocos. Cocos was introduced for me, so I can save some time, which is good because I'm running behind anyway. Say it's basically this performance portability layer. It's aimed at unknown parallelism, statically known parallelism. You basically write generic code. Here's an example here where I've done a dot product. You write these functors that overload the parenthesis operator, the function call operator, with a, well, you can see there. Anyway, and then basically you call this parallel for, and Cocos takes care of all of the memory layout, all of the sending stuff to devices, and in this case would be CUDA code. You can do OpenMP, you can do all kinds of things there. As you can see, it's pretty heavily template dependent. Mini-Arrow, the code that we were porting, was basically MPI plus Cocos. We talk about MPI plus X constantly. Cocos was the X in this case. And the question arises, since you already have these device template parameters floating all over the place, what if you want to write generic code that uses Cocos? Well, now you have your own template parameters, whatever template parameters you have for whatever you're writing, and then the device parameters for Cocos, and you explicitly listing out all the specializations, as you have to do in Charm, as far as I can tell, can get out of hand pretty quickly. And I'll give an example here. Mini-Arrow Solver has 5 different ghost exchanges. Each one of them communicates a different Cocos view type. Cocos views are parameterized on the device and also on their shape, so that there's some static shape information that Cocos can use to optimize the way it sends the memory to the device. We want a entry method prototype that looks something like this. This would already be in a chair that is, or a chair array that is parameterized on the device. So if we want to test, say, 4 different Cocos devices, and that means we have 20 different explicit signatures already for received ghost data. all of which may be relevant. If you take this further from a production level code, I've certainly worked with production level codes that have 15 template parameters on one function or class, and that's enumerating all of those possible combinations would be impossible, and the code would be very unmaintainable. So that is an issue that we have with Charm++. Here is our workaround, and present this not as a you should do this, more as a hey developers, this is what we're doing. Is this what you want us doing? So I'll go through this a little more quickly than I probably should. But if you have some Cocos view that you want to communicate, and the class might look like something like this. You have a couple of different Cocos views. This one might be a n by 3 by 5 array of integers, and this one would be an n by 3 array of integers. So the area where the actual communication happens, we end up with this templated setup, non-templated entry method, templated cleanup pattern. So we have the send is a templated function, templated on the some sort of data. In this case, my data 1, but you'd want it to also work for my data 2. Then you do the setup of the receive. Then when you call the actual entry method, do receive, it doesn't have any of this, any template parameters to it. And then you, have your standard entry method trigger and clean up the receive. And so you basically start with the send, and then in your setup, you extract the data into some normal data type. Like double star in this case, double star buffers, which is here. And put it back in to your structure in your finish. And then the actual receive code is non-templated here. And you're just basically copying into the buffer from the receive. So is this ideal? I would say not. Is this typical of the effort required to make templated code work in an AMT RTS? That may be the case, because you obviously have to have some sort of hooks if you're going to send messages with function calls or with method calls. And to generate those hooks, you have to obviously have template signatures, and the way to do that in C++ is to explicitly specify them. The other bigger question is, does Charm++ even support templated entry methods inside templated chars? We couldn't figure out how to do that. I don't know if that is actually supported. Somebody can tell me afterwards. But that is an example of our need for templates. Is if we are going to use Cocos with Charm++ for our code, we're going to need templates. I mean, we're going to need heavy template support. Okay, so another issue we had that led to some significant debugging sessions, distinguishing entry methods from regular methods. So if we have this entry method in a CI file somewhere as do stuff 1 and do stuff 2, if both of them are regular non-entry methods, then, well, what happens first? Well, do stuff 1 happens, and then comes back, and do stuff 2 happens. Now suppose do stuff 1 is an entry method, and do stuff 2 is a normal method. Well, do stuff 1 gets dispatched as a message, and immediately returns, and do stuff 2 happens.
It depends on how you call it, do stuff 1. If you call it through the proxy, then what you just said happens.
But the code is written here.
Should be one after the other.
Okay. Well, then maybe this whole thing is wrong, but with this is the specific problem that I spent about a week debugging. When I copied code from the .h file to the .ci file, things that were ordinary method calls turned into calls on the proxy. So at least in the code that I looked at that was generated, bug report. Yeah. So how does the programmer who didn't write do stuff one know this? Well, we suggest perhaps a naming convention may be useful there, or explicitly invoking the method on the proxy so that it's obvious that you're calling the method on the proxy. Yeah, in short, mixing entry methods and regular method calls makes it very difficult to write self-documenting code. I guess I'll go through this a little more quickly now that we are in disagreement as to whether or not this is actually a problem.
So that entry method do stuff one, that is a structured dagger entry method is what you're saying.
Yes.
So it's actually constructed .ci.
Yes. Right. I mean, yeah, it could be either.
The structure dagger entry method,
Yeah, the complete control flow of that isn't going to finish before this side returns. So it's not that it's an asynchronous call, it's that its contents don't synchronously block the char.
Right. Yeah, and that is a problem with any non-blocking code. I think part of the problem here is you have this word serial, which can be confusing for people who are not used to charm. Let's put it that way. And I know you guys have already changed that once from atomic, which also doesn't work very well. But
I think the best keyword I have suggestion for now is C++.
That is exactly what I was going to suggest. Yeah. Actually, I almost put a bullet point in there saying maybe this should just say
literal. So we're taking suggestions.
Or literal, yeah, literal, definitely. I like that. So I guess the serial is the biggest problem there. Again, same thing can happen if you have a some function call that is actually.
Can I stop and ask you a question?
Yeah.
You said there is this confusion depending on whether the stuff one is an entry method or not. There's no confusion because if it is a structured dagger entry method, it is clearly an asynchronous call because it might block inside, so you have no right to expect that it will return before you call this stuff true anyways.
Right. Yeah.
So if it is a regular entry method, then it should work like I said, which is call returns, call returns.
Right.
But if it's a structured dagger entry method, it has to be asynchronous. Maybe what you're saying is in a structured dagger entry method, we shouldn't allow calling in line like that. We should just allow the proxy.
Yeah, maybe you should have to just say this proxy there, or a naming convention. It's not completely as simple as that because you have a case where some other method can call an asynchronous method, and even further, you could have some other method could rarely call some asynchronous method that has some effect on, say, do stuff 3. And you may not be able to find that bug until that particular rare condition happens and you have the race condition and everything. This is a problem with all parallel code, right? But I think that I should say the simplicity of the charm syntax makes it more apparent, which is a bonus in some places and a feature in other places. So how do you? There's several ways you could address this. You could avoid writing code like this, and that may be a reasonable thing. It seems funny because sometimes you just can't. But we do that kind of thing in C++. We have no-throw constructors whenever we can. So things like that. We could avoid naming conventions and just say, all right, you have to go look at this function definition. Go look up where do stuff 1 is defined and say, is it defined in a CI file as a structured dagger entry method, or is it defined in a .h file? It's probably not ideal, but it might be good. You could just use comments. Okay, so am I on time? Running out. All right. So I don't have a lot.
We would like to understand this better, so maybe I'm speaking out of turn, but a few minutes over would be okay.
Oh, absolutely. No, yeah. I mean, this is really, I mean, was our hang up to some extent, and I think the serial keyword was part of it. I was looking at, part of it was this whole getting used to the idea of asynchronous method calls. I think someone was saying Silk uses the keyword async.
That shouldn't be asynchronous method call. If it is an asynchronous method call, that particular blocker is supposed to be on the language.
I was also using Charm 6.6.1. Is that the latest release? I don't know. Okay, so that could be. I definitely was getting basically this kind of code, and the program was moving on to the next iteration with the code written this way. So I mean, there may have been something else going on there, but the serial keyword. And another suggestion was made that there could be a keyword that would force all of the entry method invocations inside to block. That might be useful for testing out code or something like that, to say, okay, if I make all of this, force it all to be serial, then, and that doesn't necessarily need to be the default mode as it is in other runtime systems, but that might be useful for debugging or something like that. Obviously, the code starts to mean something different at that point, right? But yeah, okay. So I only have a couple of performance slides, but we do have, basically, our code is tracking the MPI implementation right now. This is without any over decomposition. And also remember, I mean, I assume some of you have been using Charm for years. And this is like 2 months of work, and it speaks very well of Charm that we're able to do a port that quickly and have performance that is comparable to the original MPI version. This is Charm using Cocos, although both of these are using 2 Cocos threads. So it's using the Cocos threads interface, Cocos interface to pthreads to basically utilize hyperthreading, because cache sharing and hyperthreading that way. And that's on 2 different problem types, on a ramp and a flat panel. I'm not really an aerodynamics person, so I don't know exactly what those problems constitute, but they do constitute actual second-order viscous flow and such. So this is more interesting to me. This is looking at over decomposition and the runtime overhead. These 2 were run on the same size problem, so this is strong-ish scaling, and on the same number of PEs, so I guess it's not really strong scaling, it's kind of the same amount of computing power being thrown at it. What's interesting to me is that the runtime overhead here is very small, and you get much better load balancing. This is actually with load balancing turned off. We could probably get another few percent better if we turned on load balancing, because we got this. There's a miscommunication between me and who was the person who was running these jobs. But if we had turned on load balancing on the command line, we probably would have gotten a little bit better with these more fine-grained jobs. But you can see what's interesting here is the runtime overhead only goes up by about a factor of 2 with an increase of a factor of 4 in the number of chars that we're running. And the key here is this one is actually 20% faster, which is says good things. So next steps, we're going to do more performance analysis. Obviously, we haven't run a whole lot of tests yet. We want to really understand what the costs of over decomposition are with Charm++, and how feasible it is to really heavily over decompose our code. We want to do PAPI analysis. I know there's somebody in Charm that actually has an interface directly to PAPI, so we need to talk at some point. more Cocos devices. I didn't get a chance to talk about the problems we've had with CUDA and Charm++. I know there was some mention of a more transparent build system, et cetera, et cetera, et cetera. Request from Charm++. Compiling with CUDA for us was very hard, especially since Cocos is the one that actually needs the CUDA, not Charm++. We actually don't want Charm++ to touch CUDA. And more mini apps, as I mentioned before. So, thanks. Oh.
Were you able to test the
So to some extent, we have. We've done the checkpoint restart. Actually, one of the tests in our test suite does a checkpoint restart fault tolerance. One of them does an in-memory. It uses the CK kill node or CK die now, right? They both work fine. I think we're less interested in it because it is checkpoint restart. And we fairly well know how to do checkpoint restart, and so I mean, the message logging type stuff that you were talking about at the very beginning seems a lot more interesting to us. We have a number of collaborators that are working on almost exactly that kind of thing for MPI or for various runtimes. So.
I mean, we get mixed messages on that. The failures are not going to be that frequent, so why bother? And then secondly, the in-memory is very fast, so the checkpoint time is very fast, as long as you fit within the NVRAM or DRAM.
Yeah. So that is, we get mixed messages on that too, I have to say. Hear a lot of different things.
Any other question?
Sorry, web world.